Hey everybody, welcome to Bill Sky, the Assembly Guy, and today we're going to do something a little bit different. There's not going to be a lot of coding, but this is my absolute favorite subject. It's logical operations and how they're actually implemented down in the CPU. You're going to see actual circuitry that I've built, and then I put it here in a simulator, so you can see how you can actually build portions of a CPU, AND gates, OR gates, NOT gates, and you can even implement them into adders that add binary bits. So let's get started with logical operators. So a logical operator, what, huh? The CPU operates with on and off switches, as we all know. How is it possible to do addition, subtraction, and other mathematical operations with just on and off switches? It's weird. And logical operators like AND, OR, NOT, XOR, and many others make this all possible. And how was this figured out? Well, there's this part of mathematics called discrete mathematics, and that's the math behind logical operations. Now, we're not going to do any kind of discrete mathematics today, but if you're a computer science student, you're going to have to do it at some point. I actually love doing it. There's not it's not calculus, it's not things like that. It's more like logical thinking. And not more like, it is. And I actually enjoyed that class so much. I enjoyed teaching it because it helps students become more logically minded when they're actually writing their code. And it allows them to really understand what's happening underneath the covers. So if you have a chance to take a course like that, I know the Great Courses has one. You can also probably find some stuff on YouTube. Great subject matter. We're not going to do it today, but what we're going to do is we're going to look at the results of what discrete mathematics gives us in implementing hardware and the CPU. So the first logical operator we're going to look at today is the AND logical operator. And the AND logical operator takes two or more bits, and it really only outputs a single bit. Now right here you can see that we have a single AND gate, and that's what they're called. They're called gates. We have bit 1 and bit 2 going into that gate, and what comes out is a result bit. Now the AND logical operator requires that both or all of the bits be true or turned on for the result to be true turned on. If any of the bits going into an AND gate are off or false, the result will always be false. So they must always be turned on. And here's an example of a logical operation. The AND gate, if you look at the first picture up above, you'll see that both of the switches are turned on. Thus the output, the light bulb, is now on. The second one, the top switch is turned on, the bottom is turned off, and the output is off. With them both off, the output is also off. Now, if we turned off the top bit or the top switch and we turned on the bottom switch, it would also be off. So an AND gate simply says, are all of the bits on? They're all on, so then I will say that it's on. So let's take a look at this little example video, and you'll see that I turn on the bottom bit, nothing happens on the output. I turn on the top bit with the bottom off, nothing happens. But as soon as I turn them both on, the output bit is turned on. So very, very simple. All the bits must be turned on for the output to be turned on. Now, the AND can happen with an entire byte, or an entire word, or an entire double word, or an entire quad word. It simply takes each bit and takes the corresponding byte and compares each bit with its corresponding bit in the other byte, and then gives us a result. So in this case, from left to right, we have 10101101, and then we have 00000111, and starting from the right to left, the first bit, 1 and 1 is a 1, the second bit, 0 and 1 is a 0, the third bit, 1 and 1 is a 1, and so forth and so on. So each bit is compared, and the result is what you see there in the result byte. Now, how is the AND gate actually implemented within the CPU? Well, you could actually build this. I have. And this is a diagram showing how the AND gate is actually implemented, we have two inputs, input A and input B. Both of them are, right now they're set up as 0 volts. You can see here they go through some resistors to reduce their amperage. It goes into these two things called the transistors. Those transistors are those little vertical lines with the arrow coming out. And those transistors are actually on and off switches. They can also be amplifiers, but in this case they're on and off switches. And depending upon whether or not both A and B are turned on, current will or may not go to the output lamp below them, right above the 1K resistor. That's that squiggly, jagged line. Now let's take a look at a demonstration of an AND gate in operation. So the way that this AND gate works is that as I change the inputs, so right now the first input is 0. I'm going to go ahead and notice that the output is blank. There's nothing coming out. So I'm going to go ahead and put 700 millivolts into that first input. Now I'm going to go ahead and set it back to 0 and then put 700 millivolts into the input B, and notice the output is still 0 or off. Now I'll turn on the other one by putting 700 millivolts, and you see how the output is now turned on. I'll go ahead and turn off input B, and notice how the output is turned off even though the input of A is still on. I'll turn them both off and we have 0 output. So this is the implementation, one of them, of how an AND gate actually works. The next one is the OR gate, or the OR operation. And the OR gate, that's the symbol for the OR gate. The OR gate means that either bit, or you can have more than just 2 bits, but it's kind of normal to just have 2 bits as input. If either bit is on, the result is on. If both of them are off, the result is off. So if either is on, if both of them are on, the result is on. If both of them are off, that's the only condition where the output or the result will be off. And here's some examples of that. We have 2 bits turned on, and the OR shows that it's on. We have 1 bit turned on, which is the bottom one, and the OR shows that it's on. If they're both off, then the OR would be off. Also, if we turned on the upper bit and turned off the lower bit, it would also be on. Now let's take a look at a demonstration of this. So as can be seen in this video, I have an OR gate with 2 inputs. We turn on the lower one, it turns on. We turn on the upper one, it turns on. But they're both off, it's off. If they're both on, it's also on. Just like an AND, you can have a whole byte of bits, and you can compare those 2 bytes. So the upper byte, 10101101, and then the lower byte, 000000111. And when you OR each bit, one at a time, you get 10101111. Now what makes up an OR gate? Well, it's pretty much like an AND gate, except the power flows, the same power flows to each transistor, and again the transistor is that vertical line with a line with an arrow coming out of it. And instead of it just flowing to one and hopefully getting to the second one, you send power to both of them. And that is what gets a OR gate going. So let's take a look at a simulation of how an OR gate works. And I'm going to go ahead and turn on input A by sending in this case, let's send in 5 volts. And you can see how the lamp is now turned on. We set it back to 0, lamp is turned off. Now we're going to go to input B, turn that on. The output is turned on, the lamp is on. Now we're going to set them both on by sending 5 volts. And you can see how the output is on, the lamp is turned on. We're going to go ahead and turn them both off. And now you can see how it is off. So that is the circuitry that implements an OR gate. Now an XOR gate, or an exclusive OR, works just like an OR gate, except if both of them are on, the output is off. So if you remember, an OR gate means that if either bit is turned on, the output is on. Even if both are turned on, the output is on. However, in an exclusive OR gate, if both of them are on, it's turned off. And here's an example. Both of them are on, it's off. If either one of them are on, it's on. If both of them are off, it's off. Now, exclusive OR gates, it's kind of weird. Why would you have that? Well, an exclusive OR operation lends itself directly to binary addition. So let's take a look at a demonstration of how this works. So as you can see in this video, they're both off, so it's off. I turn on one, the output goes on. I turn on the second, the output is on. If I turn them both on, the output is off. And I'll go ahead and turn them both off again, and the output is off. So that's an exclusive OR. An exclusive OR, just like an AND and an OR, you can have a byte, 2 bytes of bits, and notice that each bit position at each byte, if they're both on, the result is a 0. So if you look at the least significant bit, 1 XOR 1 is 0, 0 XOR 1 is 1, 1 XOR 1 is 0, and so forth. Now here's an example of using exclusive OR gates, and the exclusive OR gate is an OR gate with that curved line on the input side. Using an exclusive OR gate, gates and AND gates and an OR gate, you can actually create a 1-bit adder. So it is critical in the operation of binary addition, and we're going to actually see a demonstration of this in a little while. The next gate is the NOT gate, and the NOT gate simply flips the value of the bit that goes into it. So bit 1, it only has one input. Bit 1 goes in. If it's a 1, the result is a 0. If bit 1 has a value of 0, its result is a 1. So it just flips the bits. And if you remember in 2's complement calculations, this is exactly what happens. So here's an example with the bit on, the NOT gate, the output is off. With the bit off, with the NOT gate, the output is on. So let's take a look at a little demonstration of this. As you can see in this example, it's off, the light is on, it's on, the light is off, it's off, the light turns on again, it's on, the light turns off, and you could do this all day long. But that's the simple example of how a NOT gate works. And just like an AND and an OR and an XOR, except there's only one input into a NOT, you can NOT an entire byte, and the result is simply flipped bits. So if you remember 2's complement is that you flip all the bits and then you add 1. So you could go ahead and use a NOT to flip all the bits. That's the first step in 2's complement, and then you would add 1 binary digit. So here you can see the implementation of a NOT gate. You can see that it only has one transistor. It has one input, which is down over on the left, and then that input goes into the transistor, and then the power going to that transistor is either turned on or off depending upon whether or not the input has a 5-volt value or a 0-volt value. But I think, let's take a look at the video. It's a little bit easier to see this occur on the video. So in this video, we're going to turn on the voltage to 5 volts, and notice that the voltage goes through the transistor but down. When we turn it off, you can see the light turn on. So we turn it back to 5 volts, the light turns off. We turn it back to 0 volts, the light turns on. So that's the simple circuitry of a NOT gate. So let's take a look at combined operations. What are the combined operations that you can put in logic gates? Well, by putting a simple 0 on the output side of an AND gate, for instance, on top, it becomes a NAND gate, which means it's AND, but then it's knotted. The same with an OR gate. An OR gate, you can put a little circle on the end. It's right attached to the output end of the gate. It now becomes a NOR gate. So that would be an OR with a NOT. Now, why do that? Because we do a lot of NOT implementation when we're designing circuitry. And instead of having all those triangles sticking everywhere, we just put a little 0 at the end, and so we know that that's a NAND or a NOR. So what are some of the uses of all these gates? Well, I mentioned this earlier. One is a single bit adder, where you can have 2 inputs, which is input A and B. Those are the 2 bits. And then you can have a carry, which might be coming from another bit addition. And that's also input into that single bit adder. And I think we should go ahead and take a look at an example of that so you can see it actually working. So let's take a look at this video. What's happening? I turn on the first bit and we have a 1. I turn on the second bit, we have a 0, but it goes to a carry. We turn off the first bit, we get a 1 again. We turn off the second bit, the sum is a 0. So if they're both on, we get a carry that goes to the next bit that we're going to be doing addition with. Now it's actually even better to take a look at what we call a 4-bit adder, so you can actually see what happens with that carry out. So in this one, the first 4 bits is bit 0A, 1A, 2A, and 3A. That's our first 4-bit number. Our second 4-bit number is bit 0B, 1B, 2B, and 3B. So that's like 1001 plus 0001. That type of thing. We have the top number on top and we have the bottom number on bottom, and we add those together. So those are the bit inputs going to each one of these packages. Now that square box is the previous single bit adder. So we've packaged those into what we call a package, which takes 2 inputs, A and B. It also takes a carry from the previous bit. So if you look on the far right, 0 goes into the very first bit adder because, you know, we want to use the same bit adder. We don't want to have to create a special one that doesn't take a carry. So we just hard code a 0 going into there. We add bit 0A and 0B together. If those are both 1s, it will then send the carry to the second bit adder. If that one creates a carry, it'll go to the third bit adder. If that creates a carry, it goes to the fourth bit adder. So let's actually take a look at this and see how this actually works in a simulator. Okay, so let's take a look at some addition operations with a 4-bit adder simulator. Now in this video, what you're going to see is you're going to see that I've got all the upper bits off, and I'm going to go ahead and turn on 1001. Then the second number is going to be 1, and you're going to see how 1001 turns into 1010 on the bottom. And the carry out is still 0. So let's reset everything. Now I'm going to take 0111 and I'm going to go to the second number, 1, and notice how it carried all the way from the right to the left. So the fourth bit is 1, but the carry out is still 0. So let's clear everything again. Now we're going to take 0111 and we're going to add 0100. And you can see that the sum is 1011. Make sure I get that right here. There we go. So 0111 plus 100 is 1011. And notice that there's no final carry out. So let's clear everything out again. And now what we're going to do is we're going to put all 1s on the top. So we're going to add 1111 plus 1. So we put all 1111 up on top. And now we're going to put a 1 on the bottom. And notice how the sum is all 0s. But then we have a carry out. That would be the carry flag in this case if we had a 4-bit adder. So this is a simulator on how a 4-bit adder can work with simple logic gates. What are some of the other uses of these? Using AND, you can test to see if a certain bit is on or not on. So if I take 11001101, and if I want to see if the first bit is turned on, I just AND it with 000000001, and if the result is 0000001, since that value is greater than 0, that means that bit number 1 was turned on. All the zeros turn off all the other bits from the leftmost number, so we can use AND to do that. You can also use AND to test to see if a group of bits are on or not. So if we have 11001101 and I want to see if the first and the fifth bit are turned on, if I AND those two together, the result is 000000001. That's not equal to 000100001, so 1 and 5 are not both turned on. You can also use AND to turn off certain bits. We kind of did this in the first example. If I want to turn off all the bits except for 101, the first and the third bit, then I would just AND it with 0000101. That turns off all the bits and just makes sure that those other two are turned on. Using OR, you can turn on certain bits or just leave them on. So if I want to make sure if the first and the seventh, I believe that's the first and the sixth bit are turned on, I just OR the number on the left with 10001, and that makes sure that the first and the sixth bit are both turned on. So these type of operations are a way that, robots do not have a whole lot of memory in them. So what they'll normally do is a bit means something like in my fictitious robot here, bit number 3 on means that the left eye should be opened up. Turning it off means the left eye should be closed. Or maybe bit number 6 turned on means destroy the world or something like that. Let's leave that one off. So we could turn off bit number 6. So by using OR, you can turn on and off bits. Actually, you can't turn off the bit. So you would need an AND to turn it off, but an OR would definitely be used to turn it on. All right, so that's the logical operations inside the CPU. We looked at gates, we looked at the operations themselves, we even looked at some circuitry on how to implement those gates. So the next video is going to be much shorter, and it's going to be the coding of these logical operators inside your assembly language program. Hope to see you there.